Hi, my name is Nimrod Sapir. I work at QSpark. QSpark is a company in the area of high-frequency trading, which is a type of algo trading. So today I'm going to speak a bit about this market, the challenges in high-frequency trading, both the technical challenges, and I'm going to speak a bit for about 10 minutes about the business side. So that's not going to be very technical, but hopefully still going to be interesting. So about me, I've been working in the HFT world in QSpark for the last 5 years. Before that, I worked on performance-sensitive systems in C and C++, mostly in the storage area. And I'm saying this because when I worked in storage, I thought I knew performance, but performance in the HFT world is a completely different beast, and I'll explain why. So, but first, what we're going to talk about. So I'm going to explain what is algo trading and what specifically is high-frequency trading. I'm going to talk about how this high-frequency trading that came in the last 20 years, how it impacts the market. I'll explain about the technical challenges we have as a company for building a trading product in this world. And I'm going to speak about how we handle those challenges. What do we do? So specifically, I'm going to talk about avoiding branching misprediction, about reducing cache misses, about our use of specific data structure for specific use cases, and about our continuous performance measurement. So let's start with some definitions. So algo trading is pretty well defined. Algo trading is every trading which is not done manually, which is done by some kind of automated algorithm without manual intervention or without complete manual intervention. High-frequency trading is more vague. Basically, it's any algo trading which has a high trading rate and has a short investment horizon. So those are not as accurate definition, but basically short investment horizon mean that if a human trader would probably buy and sell and hold for a day, a month, maybe years. An HFT algo would usually buy and sell at the same day within hours, between minutes, sometimes within fractions of seconds. And basically, HFT algos don't try to make long-term prediction of the market. Is it going to go up today? Is it going to go down? They're more about reacting to market events, understanding the market state, and making very short-term prediction, or just understanding what's going on in the market before everyone else and reacting quickly. And I'll talk about what is high rate means later on. Okay, so a bit about the market share here. So this is just an estimation. There's no real official statistics, but it is assumed that high-frequency trading takes at least 50% of the trading in stock trading market. So basically, we're talking about trading volume here, not about capital, not about the amount of money in the market. So it's not that half of the money in the market is held by HFT firms, but since the volume of those algorithms is very big, they keep on buying and selling constantly, they take a large portion of the volume in the market, of the action done in the market. And actually, that market share has actually declined. The peak years was 2009, where probably the most profitable and the biggest volume or market share those algos had. And you can see this in this graph, and this looks a bit weird because usually when automation takes over some kind of market, it usually just keeps on consuming it or reaching some peak state and remaining there. But this can be explained when you put this next to another graph of the VIX. VIX is an index of the market. It's the volatility. Basically, it reflects how much anxiety is in the market. And markets with anxiety, markets with fear are very inefficient. And because people make the wrong decisions. And when a market is inefficient, algorithms and algo traders can come in and basically live off that inefficiency. Because when you add some, bring back the efficiency into the market, you can make money out of it. So a lot of time the HFT algos consume inefficiency. You can say it like that. And just to give you an example, you see that small bump in the VIX between 2017 and 2018. This is how it looks on the Dow Jones. So 2017, you can see a very steady incline, while in 2018, it all goes berserk. The market goes down and then up and down and up again. And this adds a lot of opportunities for algo traders. So now the question arises if HFT is good for the economy. So this is quite a big debate. There are many discussions about that. I can talk about two known benefits. Maybe I'll mention first that there was a known incident called the flash crash in which the stock market crashed for 36 minutes, probably due to algo trader. It lost $1 trillion, which came back 36 minutes later. So those kind of things makes people worry about algo trading and high frequency traders. But known benefits we do have is one is lowering the bid-offer spread, which that means that buyers and sellers come closer together, because if there's a big delta between the buyer's price and the seller's price, that's inefficiency, and it's very likely that algorithms will come in and change that. Another thing that algo trading do is adding liquidity to the market. I'll show a very short example, a very simple one, called market making. So let's assume that Alice wants to buy apples, and apples are readily available in the market. There are apples anywhere, but she doesn't have funds to buy apples. She needs to sell something first. She has dragon fruits. Not a lot of people wants to buy dragon fruit. So basically, she doesn't have a buyer. So one thing she can do is to wait. And if she's waiting 6 hours, maybe 6 hours later, Bob will come in and buy those dragon fruits. But think about all the transactions waiting for this to happen. She wants to buy apples. Maybe the person she's buying apples from wants to use that money to buy something else. So the market is pretty much stuck on this transaction, or at least that specific, those specific funds are waiting. In comes Carl, the trading algorithm. So Carl is willing to buy those dragon fruits immediately, wait for 6 hours, and sell them to Bob when he comes in. So actually, Carl here added liquidity to the market, enabled a lot of transactions to happen. It seems that Carl didn't make any money here. He bought and sell for the same price. But actually, each transaction has a fee in the market. So the market earns. And since, in that case, Carl is a market maker, the market can reimbursing him. He can give him a rebate for the risk he took. And just notice that Carl took a very big risk because he doesn't know that what will come in. And also, the algorithm also doesn't know that the price of dragon fruit wouldn't drop by that time. So basically, you need to take very calculated risks because you can lose everything with one bad trade. And also, assuming he does want to make those trades, he likely to have a lot of competition. So he needs to beat all the competition to the market. So just a bit about what fast means in our world. So this is vague and constantly changing. At the start of the 21st century, if you could react to market event within seconds, you would be considered high-frequency trading. Today, we're talking about microseconds. So microsecond is not a lot. Light travel for 300 meters per microsecond. Here in the picture, you have Grace Hopper. She developed the first compiler, and she's holding a microsecond. That's a cable of 300 meters. So you can really run an HFT rig these days from the cloud, from your own data center. You can even search for the building closest to the stock market. You have to reside inside the market, inside the stock exchange. So just as an example, New York Stock Exchange, they have a data center in Mahwah, that's in New Jersey, and you can rent space there. It's very expensive to get a rack there, but so probably most of anyone in this data center are part of the HFT ecosystem. And basically, you would think that there are some differences in latency for different people there, because this is a big data center, so at least they have to fight for the closest server to the center to get the lowest latency. But actually, there's very strict regulation here, and New York Stock Exchange actually has to give each and every one of those servers the same cable length. And the same state. From what I heard, even the coilness of the cables is being evened out because, of course, light travels slower in coiled cable. We all know not to coil out cables. So basically, in this crazy world, things are pretty much evened out, at least inside a single data center. Which means that the competition inside each and every one of the traders' technical stack. There are some differences when you talk about trying to move data between different data servers, between New York Stock Exchange and NASDAQ, but inside your own data center, it's up to your hardware, how to your network cards, up to your code. So I want to talk about the challenges, and I'm going to start with this quote. This is from a very good book I read once. It's a very anti-capitalist book, but it basically talks about a river of money you can find and collect bucket loads of cash from. And a lot of people think about algo trading, about high-frequency trading maybe, even about the stock market as exactly that. Just find that place, bring your bucket and collect money. From my experience, it's closer to jumping into fountains and collecting pennies out of the bottom. Why is that? So basically, a good trading algo should have a very good logic that is profitable. It should have an infra that provides all the trading infrastructure that logic requires, and it should be very, very fast. Nothing will save you if your logic is misguided or if you're too slow to react. Just for an example, Knight Capital used to be maybe the biggest trading firm in the world. In 2012, they basically went bankrupt. They lost $460 million in 45 minutes. Why? They ran a testing logic in production. So nothing will save you here. And nothing, you don't have any market share, you don't have any brand. Nothing prevents a quicker competitor to come in and swoop everything you have. And you need to comply for very strict regulations. The regulations are there for a reason. They protect the market. But that also means that bugs could easily end up with fines. That actually happens. So, people probably think, maybe you imagine right now, this world as something like this. Like a lot of competitors all running in the same direction, and one comes in and swoop the market. Actually, I think a better analogy would be that. Everyone running, a lot of competitors, everybody running in completely different direction, and at some point you realize you're running in the wrong direction, turn around and go back. So, the market can never be accurately predicted. That means you need to be very fast, not only to react to market events, but also to understand where you're running in the wrong direction and revert what you're doing. You have a bad order, you need to cancel it as soon as possible. You have a bad trade, sell it, exit it before you lose any more money. And you're never fast enough. I mean, if you can cut a few nanoseconds from your real-time flow, your profitability will increase. If your new version is slower than the older from the old version, you will start to lose money. So taking all of this into account, this is basically the development approach in our company. We try to keep end-to-end kernel bypass. That means we are running in user space, and all of our flow is in user space. Using any kernel services in real time is too slow. No system calls, no memory allocation in real time. Also, our network cards allow us to use the buffers of the memory directly in user space, which requires specialized hardware. We try as much as possible to avoid context switching, to avoid queuing, not to transfer data between threads. All of those things are quite slow and can cause you to lose money. We try to keep a very deterministic, very static code flow, make as many decisions as possible in compilation time, also initialization time. We try to minimize branch mispredictions, and we try to make our cache work better. We use specialized data structure for specific use case, and we assume it is not faster if we haven't measured it, because we can rely on better average performance. We want low latency all the time. So let's talk about branch misprediction. So of course, every decision you do in a runtime has a performance penalty. It costs you CPU cycles. And branch misprediction is even worse, because the CPU is doing the wrong actions while it should go in the right direction. So basically, we are trying to minimize branching and get a more static flow, a more predictable flow. So we use both. We do it both by changing our logic and both by using techniques from C++. So let's look at both. Let's look at this error handling flow. So this is basically a standard error handling flow. Each component checks the input, do something, and move the input to the next component. Now, if you're using protocols, maybe you're sanitizing input. If you have a function, you check the input. And if once you forgot to check something and you got a bug, you will add an if there, and it will remain forever. You don't trust your input anymore. Basically, this works great because you find issues and bugs as soon as possible. But this adds a lot of branching, And branching also means sometimes branch misprediction, which are costly. So we sometimes go for a different design in which each component just trusts the previous component, don't sanitize packets, assume that inputs are okay as much as you can, and wait to the end and run your final logic, and something will happen. Either it works or you pay some kind of price. So this price can be different things. If you're lucky, you get an exception. If you're more unlucky, you probably get some kind of data corruption. You can get segmentation fault, terrible crashes. So this kind of flow, it's much harder to debug, much harder to implement. You'll get one component will crash because another component is broken. So it will take way longer to stabilize the flow, to get a clean pipeline of events. But once you do, you get a small amount of branches. Of course, you can just skip any check. For example, we have risk checks, we have compliance checks. Those checks make sure that we don't lose too much money and that we follow the regulation, the law. So basically not doing those checks is very dangerous and can be against the law. So we have to do that. And that also means that our risk and compliance infra is one of the most branched areas in our real-time flow, which is pretty sad, but we can't completely avoid that. Who here has ever wrote CRTP code? Okay, about a third, I think, maybe a bit less. So CRTP is curiously recurring template pattern, and I'll explain a bit how it works and show its performance benefits. So basically, this is your classic polymorphism. You have a class called order. You have specific order that inherit from public order. You have a virtual function called place order, and you will get the right function call when you call place order with a specific order type. Now, this is great. It works perfectly. That's the easiest way to do that, but it has an overhead. What is the overhead? What? Yeah, the vtable. So basically, you have to do dynamic type binding. That cost some time. When I first learned computer science, I learned C++, and my lecturer told me not to worry that virtual table has an overhead, but you wouldn't need to worry about it. Today, I worry about it. So how can I go around that? So this is how the same code looks with CRTP. This is like the simplest example I could find, but basically order is templated by actual type, and public order inherit from order using itself as the template type. So basically, when you call place order, you can do a static cast to actual type and call actual place, and the right actual place will be called because you either cast to order or cast to specific order or cast to generic order that doesn't re-implement, so it will go back to the parent. This is basically free, at least determining the type, because static cast is done in compile time. So you don't have this overhead anymore. That sounds nice, but it has a lot of complication. First, for example, you can now create a vector of orders and then put specific order into it. It's not going to work. Those are actually two different types because they template it differently. Also this gets very complicated very fast. Think about multiple inheritance, think about multiple layers of inheritance. So you might find yourself ending up with a code that looks like this. This is not a joke, this is an actual header from our code. That's my reaction to it when I first saw it. We've improved it since, but we still have a lot of those, so it gets pretty complicated. So it should be, you should see if this is the right tool for you. You can read plenty on CRTP online, that's not a new concept, and see if that's a solution that is good for your system. Okay, there's a lot more things you can do to minimize branching. You can use maps with static values rather than creating a map and adding some values. Create a static map, assuming you can know them in compilation time in some way or another, and it will work way faster. You can add compile time compilation flags. We have a settings file with all kinds of flags, and if you change them, you need to recompile. That's annoying, but sometimes you can add decision to compile time rather than runtime. So you can do that for each and every flag in your system, but some key flags you can do that sometimes. You can change your if statement, your and ors to put more predictable value first. If you have A or B, and B is false 99% of the time, probably if you'll put it first, you will get less mispredictions. You should, of course, context express all the things, but you already know that. And everything here has a cost. That could be in development time. It's definitely going to be in compile time if you're using templates heavily. It could be harder to implement and harder to maintain, but it also can cost you in runtime sometimes if you use the wrong thing, because, for example, templates add a lot of code bloat. So if it's sometimes not, it actually can sometimes degrade your performance because it didn't actually improve your real-time flow. Okay. Moving on, I will talk about warming up the cache, and this is an important part because this is something not a lot of systems do. Think about your cache. Cache misses are very, very expensive. In a low latency code, getting something into the cache costs a lot of time. Again, we need to complete our real-time flow in a few microseconds, 4 or 5. So you can't do anything which is, you try to avoid anything which is slower. This is bad for all types of cache, but L3 cache is even worse because it's a lot of time it is shared between different cores running on the same CPU. So basically those cores are constantly fighting for the L3 cache. And this gets worse by the fact that sometimes a very critical flow is also very rare. And I'll give an example. So let's say that this is our packet handling flow. So we get some packet, we update some internal data structures, we move on, we generate an event, the event goes through the pipeline, and then we need to make a decision. Do we trigger on this data? Do we send an order? Do we run some action with the market? And 99.9% of the time, the answer would be no. Why? Because we don't react to every market event, not even close. But at some point in time, we're going to say yes, and then we'll generate an order and going to execute it. Now that's the heart of our logic. That's where we want to be the most latency sensitive, because now we're doing an action and it should happen as soon as possible. But we actually have two issues here. One, when the trigger occurs, the order placement flow, the generate order, the execute order, both the code and the data structure are very likely not in the cache, because it is taken by something that happens more often. And also, the branch predictor will probably assume that this order is never sent. So it will go to the no before it goes to the yes. But that's when we want it to go in the right direction. So what can we do? We can try this flow. In this flow, we get a data, we do the exact same thing, and we decide if we want to trigger. 99.9% of the times we're going to say no, but then we move to another flow in which we ask, should we warm up? And a few times, from time to time, maybe 10 times a second, maybe 100 times a second, we're going to say yes. And we're going to generate a dummy order. And this dummy order will run through the same pipeline of actions and will be sent. But it's not really sent because that's not a real order. But even our network cards know how to get an instruction to do a warm-up and do some internal warm-up. So we can even utilize this. So basically, this runs through the entire flow we want to keep in the cache and make sure that it is in the cache. So now the order placement is way more likely to be in the cache. Will it be the L1, L2, L3? I don't know. I can't even guarantee that it will be in the cache because caches are unpredictable. I have no control on them. But it's way more likely, and you can see this in the measurements. You can see that it saves time. This sounds simple, but there are many complications here. First one, maybe before I go to some code, is that this actual logic of generating the dummy order and running it, it takes CPU cycles. So basically, you're delaying your real-time flow to do some dummy action. So is it worth it? If you'll do it every microsecond, probably not, because most of your time you'll be spending doing those dummy actions rather than handling your actual real-time flow. So there's a balancing act of how many times should I do that, and you can find this number only by measurements. But you should remember that it doesn't come for free. But let's look at side effects. So basically, we have this function, add order value. It's basically there to, let's say, sum up all the orders. And I have a G-total value, a size T, with the sum of all orders. And of course, if I'll send all orders there, I have a bug, I have a side effect that we need to eliminate because the cache warming orders go through the same pipeline, so they'll be summed up, and like 99% of the orders in some environments are cache warming, so I'll get 99 times the value I expect. Okay, let's try some naive approach. That's what you probably would do, right? If order is warming, I have add some boolean to the order, it's warming. If it is not, count it, otherwise don't count it. But what is the issue here? Exactly. So there's two issues here. First, I didn't warm up that line of code. That could be negligible in that case, but assume this if covers a lot of flow that also has some static data structures in it that are not being warmed up. That could really impact your flow. But also, as said, I added a branching. So think about a complex flow. This small branching may be worth it because the cache is maybe warming up. It's worth warming up the cache. But think about a complex flow. You probably have hundreds of such branches, And on each of those branching, the branch predictor would assume every order is a cache warming because those are most of the orders in our system. So you can actually make things worse. So what is the first rule of cache warming? You don't if on the cache warming. So basically, we can't branch on this flag. What can we do? In this example, we can use a little trick. We create an array of total values, and we use that Boolean we had before as an index of the array. And basically, we sum up the real orders and the dummy orders separately. And when we want to get the actual value, we use false. And then we get the actual sum of the real orders. But think about, so first of all, the misprediction is eliminated. We are warming now. There's maybe a small problem here that you are warming the wrong index in the array. But basically, if you think about locality, you're probably putting all the array in the cache. We're talking about array of 2 Booleans. So that's probably not a problem. But think about a complex flow you may have in your system, trying to run through it without having any side effects, avoiding each and every one of them, without branching or with the minimal number of branching, is extremely complicated. It requires major redesign. And we had to redesign our system completely to make it work. Any bug here would lead to serious issues. It happened to us. A lot of weird bugs once we started the system because we didn't realize some side effects happen. So it should be used with care. But that said, in the world of micro-optimization, this is extremely useful, extremely efficient. Because cache, it's very hard to write a code that uses the cache correctly. Okay, let's talk about specialized data structures. So I'm going to present a small data structure here that we use. Yeah. Yeah. I mean, it can. Yeah, it can. Of course, this array is not allocated in real time, and yeah, you do increase your data structure, but that's just a small increase. Of course, if you'll need to allocate a used chunk of memory, maybe your performance will be lower. So you need to think about that as well. Yeah, but the memory is in the cache. I mean, I rather have more memory cached, but in the L3 cache, than having this memory inside the RAM, when I need to load it into the RAM. Yeah, I limited by the size of the L1 cache, L2 cache, L3 cache, but I'm trying to bring this data, this real-time flow inside the highest cache possible, not to read it inside the RAM each time I put out an order. That's my objective. Yeah. Multiple what? Multiple. Yeah. Yeah, that could definitely work in some case. If you're just summing up a number, that can definitely work. We have things that are more complicated than numbers, but that's a simple example. But yeah, that in that case that could work. That's an okay. So I'm going to show one small data structure. It's called the static flat map. We also released it so you can use it. I'll give a link later on. So we have some data structures that are very complex and general, log-free map, log-free queues, and we have some simple ones. And the idea is that we don't have a single map that matches all scenarios. We build a data structure or choose data structure according to specific scenarios, because there's no one size fits all here. So I'll give a specific scenario and show how static flat map solves it. So let's say we have a multi-threaded small map, that's an STD map that is accessed by a lot of threads, and we have a lock, and we need to lock this lock and go over that map. Now, of course, this is bad sometimes, because while you're locking, no other thread can access that map. Okay, so let's try to solve that. Let's try to copy the map and go lock it and go over lock it, copy it, and go over the copy. Does that sound like a good idea? Actually, it's a terrible idea in our case, because the memory of STD map is dynamically allocated. It's all over the place. We had a map with 20 items, 20 pretty trivial items. Copying it took 25 microseconds. That's eternity for us, so we really can't afford it. So what do we need here? We want to keep that map interface, but we want to run it over a sorted array. Use binary search on the items in this sorted array, and sorted by key, of course. And basically, for small map, we will get much better performance for iterating, and definitely much better performance for copying. You can use memcopy to copy it. Will go very smoothly, as long as it's a small map with known size. This is the exactly same code, but with our static flat map. You will be able to see the code later. I'll give a link. But basically, what's the difference? From 25 microseconds, we've gone way below 1 microsecond. So this is usable now, at least in some scenarios. And we're talking about 20 elements, okay? What's the pros and cons here? So think about it. You're running a map on top of an array. So basically, you need to know the size in advance. The inserts and removal are going to be very slow, because you need to shift the entire array each time you insert and remove a new key. In our case, we knew the key. We didn't know the values, but we knew the keys in advance, so we can pre-insert the keys and then save this time in initialization. And later on, adding a new value is pretty cheap. If your map is very large, if your map has large objects, maybe other implementation would be better. But if this is a small map over in an array, if this is a small map, the copy is extremely fast with memcopy. Iteration is fast, and even searching on a small map with binary search is faster over an array than over an STD map, or even other implementation which use non-static memory. And as I said, you can find the code here and use it for your heart's desire. And I'm going to speak lastly on performance measurements. So when we're talking about ultra low latency, sub 1 microsecond, and you want to keep that low latency low all the time, we can't accept any guarantee for better average performance. There's something that should improve performance. It usually, it might not be stable. It might be good for the average case, but not necessarily optimized to give better performance, low latency all the time. I'll give a small example. There's this flags in GCC, march and mtune. We tried using it. They are basically flags that tells the compiler to compile for specific architecture, for a specific CPU. For us, it's great. We don't mind compiling separately for each and every CPU and architecture, but it actually degraded performance. Why? I have no idea. Maybe it will be different with different CPU. Maybe it will be different with different compiler. But that's the way it happened. So if I wouldn't have measured it, I wouldn't have known that. So that means that at least theoretically, each performance tweak need to be measured, each change need to be measured. But think about it. Testing an entire matrix of all possible changes is basically impossible. You wouldn't be able to do that. So this is, don't try to look into it. I'll zoom in. So basically, this is an output of one of our performance measurement tools. And this is a zoom in. So you can see it tells you each call how much the call cost you, how many microseconds each call took, the minimal amount, the maximal amount, the average, the 95th percentile. And basically, this is great if we could have it all the time, but it's basically unusable in production because it has a very large overhead. So what we're talking about, so first this system has queues, it adds use all kind of memory which add latency, but the first latency it adds that every such system needs to add is actually taking the timestamp. So basically taking a timestamp which is, in our system at least, that is accurate to a 1 microsecond takes 10 nanoseconds. If you want to be more accurate to get 150 nanoseconds, now you have to pay 50 nanoseconds. That's annoying because the more accurate you're trying to get with your timestamping, you get a bit farther away. So this is almost ironic, but it also makes sense. So what we have to do is separate our lightweight real-time counters from the ones used in production. So what you have to do is just put a small set of counters running in our system, in production system, get some kind of measurement of which version is better. Is this better or is this better? Running it for real-time flows. If we have an issue, we can use more intrusive counters to try to detect the specific bottleneck. And then once we think we've fixed that bottleneck, because that's very hard to determine, we can run it again with the standard checks, and we can see if we improved the performance or maybe we degraded it. So basically, this is very tedious, pretty hard to do, but that's what you must do in those kind of systems. I'll end with a small disclaimer. You already know that premature optimization is the root of all evil. That's not me, that's Donald Knuth. Premature micro-optimization is plain stupid. So use those, every method shown here with care. Each one of them has serious costs. It could be, as I said, harder to debug, harder to implement. It has pitfalls. It has hidden bugs. So do use in care and only when you think that micro-optimization is actually needed. Thank you. We are hiring in Tel Aviv, so if you know any C++ developer looking for a job, and this is my email and LinkedIn address, and again, the link to the static flat map. Automatic checks for performance. Partial. We can get much better in this area, but that's definitely something you should have. Well, you can, first of all, you can assume that even if you're running in non-production, the difference between different version will behave similarly, even if in a slower CI environment. But basically, it's very likely that if you're running, for example, your CI inside a VM, inside a Docker, some of those things you wouldn't see until you go into production, or at least do some kind of QA testing that actually tries to do a regression with full production environment or production-like environment. And you'll need to go back and find those things later on. I mean, not everything you can find in your CI, but basically if you use the same method of taking a few checkpoints and comparing them, there's a good likelihood that VM environments, CI environments, when it comes to efficient logic, not to things like CPU or caching or things that are more platform related, will behave similarly. Yeah. Yeah. Well, not of all of those misprediction can be statically removed. I mean, there are some checks that are more likely to happen than the other. Basically, I think also we don't really trust ourselves all the time as developers to put every check in a way that will not cause a misprediction. Because as I said, if you add A and let's say this is packet is doing something, let's say the packet is this type of packet, which is very likely, and then it has this problem. So it will go through that flow, even though eventually that there's no problem there. So if you do specific checks for likely scenarios, you still have a misprediction by adding that. Again, you can, and also another thing is that it's unmeasurable, those things. So you can't really add this check and say, well, is this check make things worse? Because we're talking about sub-nanoseconds. So you don't have any tool to measure that. So you basically need to work with your development technique rather than trying to measure those kind of things. Some things like caching is completely measurable, but removing a small branch, you'll never know if you improved anything. Yeah, but that's like one branching out of, I mean, you can compare it if you do an entire redesign and then check it. Yes, if you remove one misprediction, then maybe you'll catch it, maybe not, and maybe it will be mispredicted in the wrong time. So maybe it still gives the right prediction 99% of the time, but you're worried about that 1%. Well, basically, we use Linux. We could probably use any flavor, any stable and flavor of any flavor that we find to be more efficient. I think we use different flavors on different machines. But basically, we try to avoid in real time to use kernel services, which I think eliminate at least some of the overhead that different flavors could have. So if you don't go to the kernel, there still could be a difference between different flavors, but it's smaller than a system that uses a lot of kernel services. Yeah. No, and it's extremely hard. And again, our network cards allow us to, well, there's still a kernel over. There's always some kind of kernel overhead, but our network cards allow us to bypass this at least partially by sharing the memory buffer inside the user space. But implementing everything in the kernel is probably terrible. You're talking about multi-threaded environment. It's extremely hard. I mean, not sure if it's doable for at least for a general case design. Yeah. Not not necessarily. I mean, each system we buy need to pay for it, and the IT expenses are very large. But let's say it's our most profitable machine, or we feel that the extra CPU power will give it that edge to be more profitable, because some of our systems are more sensitive to that change, some systems are less sensitive, or some systems are not profitable enough to spend that money. So it depends on the system, basically. But yeah, we always look at the newest hardware as much as possible. Yeah. I'll give the simplest example. When you're doing sell, and so you may be selling a stock, or you may be doing short sale on a stock if you don't have a stock and you're selling it, and it's basically the same flow, but you need to say if this order is a sell or sell short, and that is something that regulators track, and you can easily do something wrong because you're running in a multi-threaded environment that sending orders in parallel, so you need to follow up on this. So if you do a wrong marking there, you might find yourself paying a fine. So again, doesn't mean going to come in and close the company. I mean, bugs are something that happens to companies. It's not something that is unheard of. But there's some kind of price tag to this kind of behavior. Okay. Thank you.